Hello, my name is Rick Hammond, and this presentation explores the impact of shifting cultivation, also known as slash and burn agriculture, on soil health. We'll look at the key physical, chemical, and biological changes that occur during and after cultivation, and explore strategies to make these systems more sustainable, especially under modern pressures like land scarcity and climate change. Shifting cultivation is a traditional farming method used across tropical and subtropical regions. Farmers clear small patches of forest, burn the vegetation, and cultivate the land for a few years before allowing it to regenerate. Historically, long fallow periods, sometimes decades, help the land recover. However, pressures like population growth and land use regulation have shortened these cycles, prompting concerns about soil degradation and sustainability. This review aims to answer two main questions. First, how does shifting cultivation affect the physical, chemical, and biological health of soils? And second, what sustainable management strategies can help mitigate negative impacts? By examining current literature, I want to identify both clear trends and critical research gaps that must be addressed to sustain shifting cultivation in the future. There are two general models of shifting cultivation. Traditional systems allow long fallows and minimal interference, while rotational systems involve shorter cycles and more frequent clearing. These shorter cycles, driven by demographic pressures and land tenure issues, reduce the land's ability to recover naturally. However, integrating agroforestry, nutrient management, and soil conservation into rotational systems can offer a path forward. Fire plays a key role in shaping soil's physical properties. In the short term, burning can improve soil structure by increasing aggregate stability. However, it also causes water repellency and heightens erosion risks, especially during the first rainy season after a burn. These changes are typically shallow, affecting the topsoil. Interestingly, bulk density, or how compact the soil is, often remains stable unless fire intensity is extremely high. Chemically, burning vegetation during shifting cultivation releases nutrients into the soil. This happens as organic matter is converted into ash, which contains readily available macronutrients such as phosphorus, potassium, calcium, and magnesium. For instance, studies have shown that phosphorus concentrations can rise by more than 50%, and calcium can more than double shortly after a burn. This nutrient flush often causes a rise in soil pH, temporarily making the soil more alkaline and improving nutrient availability for crops. In acidic tropical soils, this can provide a critical fertility boost. However, this effect is short-lived. Within 1 or 2 growing seasons, nutrient levels return to pre-burn conditions. Despite the short-term gains, long-term soil fertility is at risk. Fire reduces key elements like carbon and nitrogen, which are essential for soil structure, nutrient retention, and microbial activity. Soil organic carbon can drop sharply after burning and takes a long time to recover. Recovery of carbon and total nitrogen requires over 10 to 15 years of fallow to return to pre-burn or mature forest levels. Cation exchange capacity outcomes vary by site and soil type. In some studies like Fashin 2021, cation exchange capacity decreased following fire, while other research found little to no change depending on fire intensity and post-burn management. Regardless, the potential for reduced nutrient holding capacity can create challenges for sustaining agricultural productivity. Biologically, the soil undergoes dramatic shifts post-burn. Bacterial biomass drops initially, but often recovers within months. Fire-tolerant species like firmicutes dominate right after burning, while groups like proteobacteria and actinobacteria dominate later. Fungi, especially mycorrhizae, are resilient during fire events and continue to aid in nutrient uptake and maintaining soil structure. This microbial recovery is critical for long-term soil resilience. The sustainability of shifting cultivation hinges largely on fallow duration. Short fallows under 5 years don't give soils enough time to regenerate, leading to nutrient depletion and crop yield decline. Recovery of essential properties like carbon and nitrogen requires at least 10 to 15 years. Land availability and population pressure make this difficult, but strategies that enhance soil recovery during shorter fallows are urgently needed. To extend soil productivity, various strategies can be used. Combining compost and ash improves both microbial diversity and crop yields. Agroforestry, or planting trees alongside crops, enhances soil cover and nutrient cycling. Other effective tools include erosion barriers, mulching, and crop rotation. Managing fire more carefully, such as burning during moist conditions, can limit damage. But even more crucial is working with local communities to co-develop these practices and make them practical on the ground. Looking ahead, Arunrat highlights the potential of using technology like UAVs, remote sensing, GIS, and soil sensors to monitor fire and soil health across scales. These tools can offer both broad and detailed insights. Just as important is research on socio-economic factors, like how shifting cultivation supports livelihoods, culture, and food security. By combining the ecological and community-based knowledge, we can co-design systems that are both sustainable and equitable. To wrap up, shifting cultivation remains a complex and evolving land use practice. It is still a critical livelihood strategy for many indigenous and rural communities across the tropics and subtropics, providing food security and maintaining cultural traditions. However, its long-term impact on soil health is not uniform. It depends heavily on factors like the intensity of fire used during clearing, the duration of fallow periods between cultivation cycles, the specific soil type, and how the land is managed during and after cultivation. While fire can offer a short-term boost in nutrient availability by raising the soil pH and making macronutrients more accessible, these benefits can be outweighed by long-term losses in soil organic carbon, nitrogen, and changes in biological activity if fallow periods are too short or if fire is used too frequently. Inadequate recovery time leads to nutrient depletion, soil erosion, reduced crop productivity, and overall land degradation. However, this does not mean shifting cultivation is inherently unsustainable. Research shows that with sufficiently long fallow periods, often 10 to 15 years, many soil properties, especially biological and organic indicators, can return to near natural levels. Sustainable adaptations such as integrating agroforestry, using compost and ash as soil amendments, and applying erosion control measures can enhance soil recovery and even extend cultivation cycles. Looking ahead, we need a more holistic and interdisciplinary approach, combining traditional ecological knowledge with modern scientific tools, like remote sensing, soil sensors, and microbial analysis, can give us a clearer understanding of soil dynamics and help tailor land use strategies to specific local conditions. Furthermore, future policies and research should incorporate the socio-economic dimensions of shifting cultivation to ensure solutions are equitable, culturally appropriate, and ecologically sound. By embracing this balanced approach, we can support both environmental conservation and community resilience in regions where shifting cultivation remains a cornerstone of rural life. Thank you for watching. Please feel free to follow up with any questions or to review the full list of sources here. Thank you.